Just a second. Here. Yeah. All right. Perfect.
Yeah. Can you hear us now?
Yes. Yes.
Okay. Perfect. Yeah. Sorry. I hope the beginning of my talk was self-explanatory. I will just take it from here. But I hope you you got the gist of what I wanted to say. Like, we are interested in these puzzles, and I'm not really interested in these proximate explanations, because like in each case you could ask yourself, why do we have these specific emotions? Why do we have these kinds of social norms? Do we have arbitrary social norms? Like, are there any restrictions on the social norms that we could have? And those are the kinds of questions that we are interested in. Yeah, so let me refine our basic question on an ultimate level. Like, how can we make sense of some of the social, of the puzzling social behaviors? And yeah, and we use different methods to approach these questions. Like, I myself am mostly a modeling person and mathematical analysis person. I do some simulations, but obviously Ben is one representative who would work more with behavioral experiments, and we also, to some extent, analyze online data. Yeah, so the structure of this talk is as follows. Like, I mean, always when you give a talk, like, you need to think what should be your main message. Who is your superstar in this talk? My superstar in this talk is evolutionary game theory. So this is what the take-home message should be. Like, what is this framework? What is it good for? And I believe, as some add-on benefit, I will talk about 3 more projects specifically. Like, this will be population reciprocity, social norms, and modesty. Yeah. So yeah. Like, so I wanted to give a very brief introduction on what is evolutionary game theory, and like, I believe some, or perhaps even everyone here, already knows what classical game theory is, but still, like, perhaps it's nice to compare those two. So, like, usually, like, when you want to do, like, we are interested in social behavior, and social behavior, often the optimal behavior for you depends on what another person did. And once you have this dependence on what other people did, like, the perfect framework for these types of questions is game theory. And like, if you want to come up with a game theory model, you need to define different things. Like, first you need to think about, okay, who are the players in this game? And what is it that the players can do? And what are the payoff consequences of the players' actions? So those are all things that we need to define. And in addition, like, depending on how complex the model is, we might have to define additional things like, what do I know when I move, and like, what is the order of moves? And like, once you have specified these things, you have a game. And once you have a game, the next step then is to solve the game, which kind of is to make a prediction of what will happen in this game. And like, the usual solution concept is then you calculate equilibrium. Like, just to have an example in mind, if you think of this doing favors game, this game could be represented by such a matrix. Like, for example, you choose a row in this matrix. You choose either to cooperate or defect. Your co-player also chooses to either cooperate or defect, and these numbers in this matrix will be payoffs. Now, so this is the full specification of the game. Players move simultaneously in this game. Now you have to think, okay, what is the solution of this game? And now, if you look at the specific payoff matrix, you see, like, you could choose cooperate or defect, and you don't really know what the co-player will do. But you see, like, if the co-player chooses to cooperate, defect gives you a higher payoff. But even if the co-player chooses to defect, defect still gives you a higher payoff. So this game is actually quite easy to solve. And the solution will tell you, yeah, that mutual defection is the only equilibrium in this game. And now that we are here, I can actually give you a definition that I should have given you before. Like, I always said we are interested in puzzling social behavior. And now you might ask, okay, what is puzzling social behavior? And my working definition here is like a behavior that we see in the real world, but that doesn't seem to be a natural behavior, where it's hard to explain why we even see this behavior. Okay, so this is what people might call classical game theory. Now to evolutionary game theory. Yeah. So also, if you want to set up an evolutionary game theory model, like, you have to actually need all the components that you already need for the classical game theory model. Like, you need to define what actors, what are possible actions, and so on. But in addition, you also need to define, how do people come up with new strategies? Like, how do they learn? Like, in classical game theory, you just assume that people somehow magically arrive at this equilibrium. In evolutionary game theory, you assume that you have players, they may not play at equilibrium yet, but over time they learn and they adopt new strategies over time. And so your model then needs to define how do players learn new strategies in this game. And once you have defined these components, you can compute like what will happen in the long run. Like the picture that comes here is yeah, the following. Like if you think again of this doing favors game, like how evolutionary game theory people would think about it is like they would have this population of players. Each player plays a strategy at the moment, which can be either blue for corporate or red for the effect. And then they randomly play against each other, get expected payoffs. And then over time, they compare the payoffs with each other, and then they learn new strategies. And in this case, it's true that usually the factors will have a higher payoff than the corporators. So what you would expect in this case is that in the long run, the population looks like this. Like the number of the factors increases over time. Yeah, so these are the basics of classical and evolutionary game theory. Now we could make things a little bit more complicated because the student favors game is really a little bit trivial. Yeah, so a little exercise for you actually, like now there's a different game, the stack hunt game. I have already defined the game for you, like here's the payoff matrix, it tells you everything you need to know about this game. The question now is, what is the solution of this game? Like if you were to play this game, what would you predict would people play? And the logic that I previously used, like I assume, like let's assume my co-player plays the first action, like stack in this case. Oh, the best thing that I can do then is also to play stack. But I don't know, like the co-player could also play hare. But if my co-player plays hare, actually the best thing now is to play hare. So the logic is now a little bit more complicated than it was before. Like in the language of game theory, previously we had a dominated action. Like no one ever wanted to cooperate. But now here in this game, there is no longer a dominated action. So you need a slightly more complicated solution concept, like now really Nash equilibrium. And if you do this, you will find out that there are at least two Nash equilibria. There are actually three, but it's not so important. Like the third one is mixed. Like here, a reasonable prediction for this game would be that both players play stack or both players play hare. Yeah.
But the clarification on the last game, why was it called Doing Favors?
Oh, I just made this name. Yeah, please don't read too much into this. Doing favors, I mean, the interpretation is, if I do you a favor, I pay a small cost and you get a high benefit. That's how I constructed this matrix.
I see. But in the solution, nobody's doing favors.
That's right. That's the sense summary of this game. Yeah. Yeah, perhaps I should have called it the not doing favors game. Yeah. Anyway, so this is the classical view on this game, and now another exam question. Okay, think about this game like an evolutionary biologist. What would be your expectation? What happens in this game? So this is your initial population. What would you expect happens in the long run? Yeah, I mean it's actually not clear, but what happened in this case is actually it's not uniquely defined. Like two things could happen. Over time, it might be that everyone learns to play stack, and that would be then an equilibrium of this evolutionary game. Or it might be that everyone learns to play hare. And which outcome you'll see in the end will depend on your initial conditions. Okay? Like if in the beginning, most of the people play stack, probably in the end, everyone will play stack. If in the beginning, most of the people play hare, in the end, everyone will play hare. Yeah.
But sorry?
Yeah.
But like fluctuations would always drive into one or the other, right? Like you couldn't stay fixed at like a equal, like a equally sized initial condition.
That's right. Like, I mean, things are a bit more complicated. Like you would have to, like now I would have to tell you a little bit more. What is the exact dynamics that I look at? Like, do I, for example, look at the stochastic dynamics where things can fluctuate naturally, or do I look at an ordinary differential equation model of how evolution works? But yeah, usually you would expect that if it's for any reasonable evolutionary process, you would assume that over time you move more towards these pure populations. All right, so I just want to convince you that these two approaches, like the classical game theory and the evolutionary game theory, are two complementary approaches to make sense of social behavior. Like it's not that I would say evolutionary game theory is better than classical game theory or the other way around. Like I see them as complementary. Yeah, sorry. Yeah, and also perhaps you've got this impression that most of the time they actually give very similar predictions. Like here, for example, you had two equilibria, and also here in the evolutionary approach, there were two possible end states. So it's not that they usually give completely different predictions. They often, but not always, make similar predictions. Like, for example, one thing that could happen in an evolutionary model that cannot happen in this classical setup is that things do not converge. Like you could have, for example, cycles going on forever. And that you wouldn't see in an equilibrium model. Yeah, and what I also find interesting is like they make different assumptions on how smart people are. Like for this classical game theory approach, like you somehow assume that people arrive at an equilibrium, and for that you need to assume that they understand the rules of the game, that they can make sense of what the opponent would probably do, and that they are able to optimize their actions given this knowledge. And in evolutionary game theory, like you can do with very few assumptions. Like you do not even need to assume that people are aware that they are playing the game. Like much of it could be subconscious learning, or like some behaviors are also genetically encoded. So there is just a case that the unfit individuals die, and the individuals with a good strategy have more offspring. So their individuals really do not need to understand that they are playing the game. So to some extent, you can even see evolutionary game theory as a justification for classical game theory. Like evolutionary game theory would sometimes tell you how people arrive at this equilibrium. And yeah. Yeah, and yeah, evolution models are sometimes a little more challenging to analyze. Yeah,
just for clarification. So in the evolutionary game theory model, once it's evolved, can it be reversible?
That again depends on the kind of model that you look at. Like if you look at the deterministic model, like for example, with modern and differential equation, once you are at a fixed point, you cannot go away anymore. But if you look at the stochastic model, where like there can be mutations and noise, you can switch between different equilibria in the long run.
Okay.
Yeah.
To what extent? You describe them as complementary views, but my intuition would have been that this is sort of like a subset of the evolutionary game theory view, in that it's like you're just looking at the like fixed point or time invariant kind of things, or something like that.
I guess you might interpret it that way, especially like there are actually really close connections between those two viewpoints, because like there is a very well-known dynamics for this evolutionary game theory, which is called replicating dynamics. And for this dynamics, you can prove that some population state is a fixed point of this dynamics, almost if and only if it is an Nash equilibrium. So there are really nice connections between the two worlds. But so formally, you could see classical game theory as a subset of evolutionary game theory. I guess in practice, it's really not, because like evolutionary game theory models make some simplifications usually on some other side. Like to be able to analyze all these dynamics, usually the games that we look at are simpler than what you would usually look at in a classical game theory game. All right. Yes, so this was my primary in evolutionary game theory. If yeah, so I really hope my main message, my main superstar in here. Yeah, now I will talk about 3 applications. Yeah, the first application is population reciprocity. So, like coming back to this doing favors game, like here we had like both classical Nash equilibrium and evolutionary game theory told us that in this game we don't see favors. Yet if you think of real life, we see people doing favors all the time. So probably there's something wrong then with this model. Like probably this model misses something. And like one idea that we could have is like, well, in practice, people meet more than once, and usually when we do favors, like I do a favor to my friend, but I know like next time I need a favor, I can ask my friend. And that's how it works. And now the question is, okay, like if this is your intuition, how do you translate this into a game theory model? And like for a specific case of people usually meet more than once, there's a very well-defined game that is usually used to represent these kinds of things. It's a repeated presence lemon. That's the idea that you don't play this game only once, but you play it over and over again. Like after each round, you have another round where you again make this decision. And what is interesting then is that, I mean, what is interesting about this repeat game is that now strategies are more complicated. Like in the simple doing favors game, there were only two possible things you could do, corporate or effect. But now in this repeated game, like strategies become much more complicated because now a strategy needs to be a rule that tells you what to do in every possible moment. And this rule could be very complicated. Like it could tell you, like corporate only if it's the third round, but only if the co-play corporate in the previous two rounds. And like it could be arbitrarily complicated. Like one of the best known examples of such a strategy is actually a very simple one. That's this tit for tat rule, which is just in round one you corporate, and in all other rounds you just do what co-play did in the previous round. And if you think of this specific strategy, like you could ask yourself, well, is this perhaps an equilibrium of this game? And there it again depends on which notion of equilibrium you use, like do you use Nash equilibrium or sub-imperfect. It would actually be a Nash equilibrium to use this game. So if I know that my co-player plays tit for tat, and if there are no errors, and if I don't, if you ignore technical details, then actually the best response to this strategy is also to play tit for tat. Yeah, but tit for tat is not only possible equilibrium, like there are many, like there are uncountably many. Like there is this famous theorem in economics that tells you like almost any reasonable outcome that you could think of this game can actually be sustained in an equilibrium. Yeah.
When you say tit for tat is the best response to tit for tat, what do you mean? Because like if I just had a always cooperate strategy and fight against tit for tat, it would do the same thing.
It's a very good question. I was slightly imprecise when I said that. What I should have said is tit for tat is a best response to itself. And that's all that you need for being a Nash equilibrium. Like, you need to have this property that against my strategy, there's no other strategy that does better. Yeah, and now I gave you the classical view. Now I should give you the evolutionary view. Like, what happens if you now look at evolutionary dynamics of this thing, and if you simulate this? I mean, what you will often see is that, like, you often see cooperation in it. Like, in the end, strategies like not tit for tat, but like wind stable shift, for example, would evolve, and then you would see a lot of cooperation. So, in some sense, this model does a good job in resolving this puzzle that we started with. Like, if our puzzle was like, why do we do favors? Now the puzzle is kind of resolved because, like, now we can make of it in an equilibrium. Like, this is an equilibrium of a game. Yeah, and now, I mean, after telling you the basics, I want to tell you a little bit more about like current research, specifically the research that I've done. Like one thing that you might find a little bit boring about this the previous game is that we play the same game over and over again. That's perhaps not what happens in real life. Like the games that we play change in time, usually. Also, like sometimes we actually have our actions now actually have some effect on the games that we play in the future. Like for example, if you think of the tragedy of the commons, like if we in the race collectively defected in this round, this year, like the game that we play tomorrow might be a very different game from now. And so that's something that you cannot capture with the usual repeated business lemma, but you can capture it with what is called a stochastic game. And the idea is that games can change in time. So the typical illustration would be this. Like, for example, the players start in this game, but as soon as someone infects, they move to a different state. So in the next round, they would play this game. And once you are in this game, there might be some stochastic transition rule that brings you back. In this case, if everyone cooperates, you play the good game again. And now, if you think of this specific scenario, what makes this interesting? Like, if you understood cooperation in the repeated business lemma.
Do you want us to press the arrow?
Yeah, please.
Right?
Yeah, I'm really sorry.
Sit there and whenever you do that.
Yeah. Yeah, what is really interesting now about this scenario, like if you understood the repeated business lemma, there, like tit for tat was an equilibrium, because tit for tat has logic, whatever you do to me now, I can do to you tomorrow. And this is actually no longer true in this game, because if you defect to me now, the game that I play tomorrow is actually a different one. So I cannot do exactly the same thing to you tomorrow anymore. So it's no longer obvious whether you would actually get cooperation in such a setup. And so what we did is we did run some simulations for games like these. And like what we did is like, for example, we did run simulations if people only play this game over and over again. If people play this game over and over again, and what happens if now you have these transitions between games? And what we found is the following thing. Yeah, perfect, thanks. Like what was really interesting to us is that if people only play game one all the time, you hardly see any cooperation. So here there is time measured in, like here we ran an evolutionary simulation and we just, the x-axis shows time, like which strategy players use at which time step. The y-axis shows cooperation. So what we recorded is like how much cooperation do you get as a function of time. And if people only play game one over and over again, you hardly see any cooperation. People only play game two over and over again, you see even less cooperation. But if they play the stochastic game, you see a lot of cooperation. And the reason, the intuitive reason for this is because actually you can almost think of the stochastic game as a game with three players. Like actually nature is the third player. And what nature does is like if someone defects, nature punishes these players by selecting a worse game. And whenever you have this transition structure that nature punishes bad behavior, actually stochastic games help cooperation. Yeah.
Can you not integrate the outcome from the other game into the chaos from the first game? I mean, it seems a bit like the effective cost of the effect is actually a different one. You're playing it's -1, but it's not -1 because you actually pay an additional cost from switching the game.
That's right. Yeah. So yeah, that's right. So this, like here, there's a twofold cost of defection. Yeah. And I mean, you suddenly go to a different game. Yeah.
Yeah, I'm just thinking, just can integrate this cost into the first game and simplify.
Yeah. The question is whether there is an equivalent repeater game that will capture what this stochastic game does. Yeah, I would have to think about this a little bit.
Isn't that the theorem that like any extensive form game can be collapsed to like a massive standard form game?
I believe that's only true for finite game, like if there is a finite horizon.
Okay, yeah. That's it. That's fine.
Okay, yeah. So the other thing that we were thinking about is like here we had games in changing environments. Like another thing that we were interested in is actually like in all these examples that I've given you so far, the game has been symmetric. Like we had the same cooperation cost, we had the same benefit of cooperation. Now you could think about like what happens actually if these things are no longer symmetric. Like and what we used here is no longer a prisoner's dilemma or a doing papers game, but rather a public good game. So what we looked at here is like, for example, you have 3 players. They have different endowments. So at the beginning of each round, players get some money. They can then decide how much of this money they put to public pool. They know that their contributions are multiplied by some factor. Here, this factor is called R. And the players can actually have different factors here. Like, and the rules are such that whatever is then in this pool is evenly split among all players and then given to the players, back to the players. Okay. And the rules, like how you choose these parameters, they are such that the game is a social dilemma. Meaning that if you only play this game once, not contributing anything is the Nash equivalent, like the unique Nash equivalent. And like if you think of this game, also this is now interesting because like tit for tat is does no longer work the way it did before in the repeated princess level, because like it's no longer true that I can hurt you in the next round the same way as you could hurt me, because like we might be very different players. Like you might have a much higher endowment than I. And now, so a crucial question then is like, how unequal are we, and how does inequality actually affect whether we can get cooperation started? And for simplicity, what we did here is like we kept the players' productivities fixed, and we asked for given productivities, how should we allocate endowments to the players to maximize cooperation? Yeah, and so this is what we see. Like we consider 2 different cases. Like one is the usual standard case of a symmetric and linear public good game where everyone has the same productivity. Like this means that my contribution to the public pool is multiplied by a factor of 2, and that's the same for everyone. And then you can ask yourself, okay, how should I allocate endowments among these 3 players such that you get full cooperation? And this is the picture that you get. most people might not be familiar with this triangle representation. Like this is just representing all the possible ways how you could allocate the endowments to the 3 different players. Like for example, at this corner point, you would give the full endowment to player 3. Or at, for example, here, you would get half of the endowment to player 3, half of the endowment to player 2. Or here in the center, you give actually every player the same endowment. So these triangles represent all the possible ways how you can allocate the endowments to the 3 different players. And if you now calculate, okay, like for which endowment distributions is there a cooperative equilibrium, like an equilibrium where everyone cooperates, you get this blue region. And what you see in this blue region is like it's never in the corners, like you should never give the whole endowment to one player, like that's always bad for cooperation. And what you also see is like giving everyone the same share is actually always in this blue region. Like if there is a blue region in this game, it always contains this very center point. And now if you do the same trick, but now for an asymmetric game where player 1 now has the highest productivity, like if I contribute something, my contributions are multiplied by 2.9, which is really good. You see a very different picture. Like it's still true that in corners, like it will always be white. Like you should never give the whole endowment to one player. But it's no longer true that the best outcome is actually to split things evenly. Rather, you should give some of the, like you should give a higher amount of endowment to the most productive player. That's best for cooperation. And so this is the, thanks. So this is the classical equilibrium view. This is the evolutionary game theory view. Like we did run simulations for this very thing. Like for each possible endowment distribution, we did run an evolutionary simulations and just compared like what is the player's eventual payoff. And this is the figure that we get. Like here, if everyone has the same productivity, it's really true that you get the most cooperation if they also have the same endowments. But if players have different productivities, you really see the most cooperation if players have asymmetric endowment. So the most green spot here is no longer here in the center where everyone gets the same endowment, but rather it's up here. Yeah, and I mean, this is theory. All this is nice, but still you might be skeptic, like, okay, to which extent is this really true? So what we did in this case is actually we did run an experiment, a very simple one. So where we manipulated 2 things, like the endowments the players would get. So here in the experiment, it's only a 2-player game, not a 3-player game anymore, makes things simple. We manipulated 2 things, like the endowments the players would get, either equal or unequal. So it's either 50-50 or 75-25. And the other thing that we manipulated are productivities. Are they either always the same, like 1.6, or is it different, like 1.9 and 1.3? And also, like the one thing that is perhaps interesting is like there are actually 5 treatments of how this is a 2x2 matrix. Because like if you have unequal productivities and unequal endowments, you need to take care. The person with the higher endowment, is it also the person with the higher productivity, or is it the other way around? Okay, yeah.
Sorry, I didn't really get what they do the experiment. So what is productivity? What is a low and high productivity, except the factors that you?
Yeah, sorry. So the rules are as follows. Like you and like Levin, for example, you play this this public good game with each other. So in the beginning of the game, I give you some money, like for example, 50 euros to you and Levin. And then you can decide, like, do you keep this money for yourself? Or do I give some amount, like perhaps even everything, to this public pool? And you know that if you give something to this public pool, like if you contribute, for example, your full 50 euros to this public pool, it will be multiplied by this factor. So it's 50 times 1.6, so it's 80 euros suddenly. Just the rules are now that the 80s don't go back to you, but it's now equally split. So in the end, you will get back 80 over 2, which is 40 in this case. So you give your full 50, you get back 40.
Thanks.
Yeah. Any other questions? Okay. Yeah, and remember our predictions was that if people have equal productivities, equal endowment should actually be the best thing. If people have unequal productivities, actually this aligned inequality should give you the best outcome. And yeah, that's what we see in the experiment. So these are the relative contributions, and this is the generated surplus. So you see if people have equal endowment, so this is the left-hand side here, you really see that full equality, like they should also have equal endowments, then you have a higher surplus. But if people have unequal productivities, Actually, the more productive player should also have higher endowment. Like this gives you the highest class. Yeah. And so what I tried to convince you is that, like, you might have heard of this repeated prisoner's dilemma before, and perhaps you are already bored by it. But there are actually very interesting things if you look a little bit beyond the usual prisoner's dilemma. Like if you take into account changing environments, or if you take a symmetry, like it's a very exciting game. Yeah, and so this is what we have worked on. Like there are actually quite a few follow-up questions that you could ask. Like for example, like in this stochastic games setup, we have assumed that players always know in which state they are. But if you think, for example, about the tragedy of the comet, it's not true that we know exactly this is the state where we are. And also, like we assume that everyone has perfect information. Like there could be also interesting effects of asymmetry. We also like assume that if you look at these changing environments, that the changing environment is given by nature, but perhaps it's also under the control of some person who could determine which game is to be played next. Yeah, and also like I tried to convince you that sometimes endowment inequality is a good thing, that's risky. But like one could still ask, okay, what's the optimal kind of endowment inequality, and how does it depend on how players make errors and perhaps on fairness considerations. So there are actually quite a few possible follow-up questions. Yeah, and perhaps with this I should make a break because I believe the talk shouldn't last more than half an hour. I do have a little bit more material that I could talk about if people are interested in it, but we could also stop now because the superstar has already appeared. The superstar is the evolutionary game theory.
I think we can do 5 more.
Yeah.
Okay, yeah. Yeah, 5 more minutes is good because that gives me time to talk about the next project, which is social norms. And like I won't go into much detail here. I will just tell you a little bit like how people in my field think of social norms, like how do they even formalize social norms. And so the question here is like, why don't we have the social norms? Like, is there some reason? Like, are the social norms, do we have an equilibrium? Are they the only equilibrium? Can there be many equilibria? Like, even more specific in our case is like, what kind of social norms would there be that are particularly favorable to cooperation? Like if you wanted to maximize cooperation in a population, which kind of social norms would I have to put in place? And now if you want to think about these questions, like the first thing you need to have, like you need a game theory model. So you need to think again, like what are the possible objects that my model needs to talk about now? Like what is even a social norm? Like how do I want to formalize a social norm? And like kind of the definition that our field has set on it is the following: like a social norm is a combination of 2 things. Like first, any social norm has an assessment rule, and this assessment rule tells me how should I evaluate it, like which behaviors do I assign a good reputation, for example. And the second component of such a social norm is an action rule. Like given that I know people's reputations, like how should I act towards them? And now, like a typical question that the assessment rule, for example, would have to tell you. Like, suppose you see a person cooperating with someone. Should such a person have a good or a bad reputation? Like, your social norm could say, well, a good reputation. But now if I tell you, like, imagine this person cooperated with a bad person. Should this person still get a good reputation? No, so it depends a little bit on context. And so these social norms can become arbitrarily complex. Like people in my field settled on a specific complexity class, which is called order social norms. So what these social norms do is like, if I tell you a sentence, for example, like a good person defected against a bad person, should this person have a good reputation or a bad reputation? I see some nodding at least, so I believe people would agree that probably good reputation. And like I could now ask you all these possible combinations. For example, if a bad person defects against a good person, what reputation? And like there are many possible combinations that I could ask you. And you could ask yourself, among all these possible combinations, which social norms in the population would actually be natural?
Are these endogenous? In the system?
They are what we previously had as strategies. Yeah.
Okay.
Yeah.
Okay.
Yeah, and if you do the math and you calculate what are the equilibrium norms, if you want, so those norms where no one would actually like to deviate from those norms, you actually, and in addition, you would also like these norms to be cooperative with themselves. If you do this, there are actually 4,000 norms, but still you can do it, and you end up with a table with 8 different norms. So this is a table, like it's
You said there's 4,000 originally?
yeah, there are, in total there are 4,000 different norms, because like here you see like the assessment rule has 8 rows, the action rule has 4 rows. So and for each there can be 2 possibilities, so it's 2 to the 12, so it's 4,096, something like that. And now you can, for example, check what do all these norms have in common. Like for example, if a good person cooperates with a good person, the assigned reputation should always. That's always a good thing to do. And also, like if a good person defects against a good person, that's always bad. Like you should never do that. Like all norms agree on this thing. Where the norms sometimes disagree is like what should you actually do against bad people? Like for example, if a good person cooperates with a bad person, some norms think this is okay. Why not? Some norms think no, you should never do that. Yeah, and again, this is the classical approach. Then you could again ask, okay, which of these norms will evolve? It turns out this is really hard to do with simulations because, like, yeah, it's just numerically hard to do these things. But if you make some simplifications, you can do it. And usually, like one norm that would evolve is, for example, the Stern judging, which says with good people you should always cooperate, with bad people you should always defect. That's the simplest way how to represent this norm. Yeah, now there is a little bit an oversimplification in this model that I told you about. The simplification being is that all information here is public knowledge. Like it's assumed that everyone knows everything about everyone else. And also there are no perception errors. And what this assumption buys you is that, can we go to next? Yeah, what this assumption buys you is that the player's assessments will always be perfectly correlated. So this is a little icon that should represent this. What this means is that player 2, for example, in this case, has a good image of player 1. And if player 2 has a good image, everyone has a good image. And here player 3 has a bad image of player 2, and if player 3 thinks so, everyone thinks so. Okay. So in this model, it makes sense to talk about the reputation of Christian Hilbe, for example, because everyone would agree on my reputation. Now, I guess most of us would agree that real life is a little bit more complicated. Like sometimes I just don't have all relevant information to really assess a person. Also, sometimes I might misinterpret what's going on. So the more realistic picture actually looks like this. So there will be usually correlations in how I assess other people. Like most of the people think player 1 is a good person. But this player 2, for some reason, like he might know something that other people don't, or he might have made an observation error. For some reason, this person thinks that player 1 is bad. So you have these imperfect correlations here. And what is really interesting about these imperfect correlations is that once people disagree about the reputations that they assign to each other, these disagreements can spread. Because like if I think that Ben is a bad person, but I'm the only one who thinks that Ben is a bad person, and I defect against Ben, which I shouldn't. But if you observe me defect against Ben, then suddenly you think I'm a bad person. Of course, from my perspective, it was the perfect fine thing to do. Yeah, so this disagreement can spread. Yeah, and this is pretty much where the state of the field is. So one question that you might ask is like, I actually look for social norms that are even better than that. Like I do not only want them to be to sustain full cooperation. I do not only want them to be Nash. I also want them to be error correcting, or in this case, disagreement correcting. And like which social norm would have each property? Like that's a question that we would be interested in. And another question that people ask is like, what is the role of empathy in such a model, for example? With empathy, in this case, I mean something very specific. Like, for example, if I see Ben defect against Levin, and although I think Levin is a perfectly nice guy, I might have to think about like what is Ben's perception about Levin. So I need to be empathetic about how he came up with his decision. And the other thing that might play a role in this model is gossip. Like obviously here you have these small disagreements, but you would think that in a model where people can talk to each other and player 2 might learn, oh, everyone thinks player 1 is a good person, so perhaps I got things wrong. Like also the role of gossip probably is actually to reduce this disagreements. But also there, like, yeah, we don't have a good model of it. Yeah, I guess now is not a good place to start. Yeah. Yeah.
So at the beginning, you talked about relating to animal behaviors and things like that. Like, what are some examples where the mathematical theory actually has like concretely explained something about this unusual behavior that people didn't understand before or something? I mean, it seems like there's an explanation of forms of cooperation at a high level, but like at a more fine-grained level, what kind of stuff?
Yeah, that's an excellent question. The answer is it's complicated. For two reasons. The first one is like I talked here a lot about reciprocity, but reciprocity is only one possible explanation for why people might cooperate, and perhaps for humans it's a very important reason, but for animals it might not be the most important reason. For animals, one very important reason is usually kin selection, which means that I have a very good reason to help my kin. Like there is this famous saying that I should jump into a river to save 2 brothers and 8 cousins. Because like on average, then my genes are happy because my brother shares half of my genes. So if I save 2 of them, on average, I have saved 1 of my genes. Very trivially speaking. So this is a possible explanation for cooperation. Now, direct reciprocity is another possible explanation why we see cooperation. And now, if you are a biologist, it's really hard in practice to disentangle these 2 possible things. Like, for example, if you only go to the wild and you see these bats cooperating with each other, like they donate blood to each other. Like, obviously, these bats usually live together with their relatives. So it could be kin selection that is going on. But it could also be reciprocity that is going on. And there are actually quite some sophisticated experiments that try to disentangle these 2 mechanisms, for example. And especially with this bat example, like there's quite a fight between different groups. But it seems like with this bat example, there seems to be a good evidence that in this case, it's actually more reciprocity than relatedness. Yeah.
I was wondering about something that I think you might have mentioned you're working on, which is what happens if nature is unpredictable in your two-play, 2-game version.
Yeah. 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 There are 2 aspects to this. Like the first aspect is like when we run evolutionary simulations, like if we look at it from the evolutionary viewpoint, we actually don't assume that people understand nature. Like they would make observations that like they would see now I'm in a good state. I would see that my co-player played this action before, but they don't draw inferences on what is the transition in these 2 states. So that's one answer. Another answer that you might be interested in is like even if you don't look at the transitions, like at least you know in which state you are at. And for example, that's something that we didn't really look at. And interesting questions also arise, like if one player knows perfectly in which state you are, but the other player doesn't. Could this player perhaps take advantage of his superior knowledge? Or perhaps in some situations, even this one player who knows might wish to communicate to the other player. Look, we are really in this dangerous state now. We really need to cooperate. And that's something that we can look at.
I was thinking from like the perspective where we know that volatility, for instance, influences explore decisions a bit, right? So here as well, it might be that the sort of volatility of states influence.
That's right.
Like in a systematic way.
That's right. Yeah. And some stochastic games here are actually really nasty because, like, some of these stochastic games can have absorbing states. Like, if you are in a bad state, you might stay there forever. And so, in such a setup, it's actually bad to use this explore-exploit framework because once you understand the game, you might already be in a bad state and you don't return. Yeah.
Yeah, I'm curious about the way how the norms are evaluated and tracked. I don't know if you're very explicit about that, but I'm actually curious about whether that itself can also have an evolutionary element, right? I'm thinking of like that people in a more functioning society will evaluate a norm very different than in the utilitarian society, right? So like in one way you would, and I'm just wondering if that kind of meta algorithm of how to evaluate a norm will then automatically lead to different kind of stability of norm, like different norms being stable in different societies essentially, and how maybe also on a more meta level, like those different evaluation mechanisms come into place.
Yeah, that's right. Yeah, I mean, all that I told you here is actually how my field thinks about these things. And I mean, my field really has the population mindset that people are really naive, but they play some social norm and they possibly debate, and then you ask, okay, which of these social norms survive these deviations?
But it's not how we discuss norms in reality, right? Like
that's right, but you might actually argue that to some extent how we think of social norms is perhaps shaped by actually how evolution selects for social norms. For example, if you looked at this table with the leading age, actually, like with most of these norms, you would kind of agree, like a good person who cooperates with a good person, I believe most of us would actually agree intuitively that this is a good thing to do. A good person who defects against a bad person, even there, most of us would probably agree this is a good thing to do, like that this is some justified punishment, this is okay to do. So even this very naive approach gives us sometimes norms that feel very natural, I think.
Actually related to this. So also when I saw this the first time, I'm wondering, has this actually been just empirically validated, right? Because it's from 2004. So
that's right.
And so someone must have done a cross-cultural study, and you might find very interesting things where some of these strategies, you just don't see them there in any culture. And that might give new interesting insights. So there might be some reasons why some constraints actually prevent some strategy from developing in some, even though you might have checked, I don't know, other countries.
Yeah, I'm not aware of this cross-culture. I'm aware that some people did vignette studies, for example, like asking exactly the questions that I've asked. Like if you see a good person copying a good person, what do you think this is a good person? And there you see quite some overall some agreement. Like you would even see that perhaps like the norm that fits best is again this stern judging that with good people you should cooperate, with bad people you should defect. There is also some evidence from developmental psychologists that suggest that this is the norm that very young kids seem to apply, but I'm not sure how convincing the evidence here is already.
Because to me that would be very striking, right? But what if you go to other cultures and they all play the same?
Yeah.
Then it doesn't matter that you have in theory all these options, but actually there might be some other constraints.
That's right. I mean, for people that would be exciting, there's something more to look at. Yeah, we need to refine our model.
Yeah.
It's almost like physicists, like you are a theoretical physicist, and then an empirical process, you look, your model was wrong, and then, okay, you can go back to the drawing board.
Yeah. So a question from Christiane who's joining online. Is competition not more common than defection? There is also competition in the animal world, no?
Yeah, that's right. It's very interesting. Like actually, like last year there was the 50th anniversary of evolutionary game theory. Like the very first evolutionary game theory paper appeared 50 years ago, and that was exactly about the competition among stag. Like what's interesting about stag is that they have this very ritual kind of fighting. Like you know that they have big antlers, and but how they would fight is like usually they would walk next to each other for quite some while, and then they would stand in front of each other, and then they would slowly put down their antlers, and then they would start fighting. It's a strange ritual that they are doing, and you might actually wonder, like, why do they do this? Like, why don't, like, when they are walking next to each other, why doesn't a stag do this? It just kill the opponent, or at least seriously hurt his opponent. And like, what was the opinion before that paper was, well, they do it for the good of the species. Like, if the species did this, then probably we wouldn't see the species anymore. But then, like 50 years ago, there was this paper that said, no, they don't do it for the species. They do it because this is the best thing that they can do. in a very well-defined sense. Like the game that was used back then is this hawk-dove game. And what this game suggests, like if everyone was a hawk and if everyone wouldn't follow this rule, like you would just run away. But if everyone runs away, then probably you would like to be a hawk. And so if you then do the math and ask, okay, where's the equilibrium of this game? You see the equilibrium is a mixed population, like some are hawks, some are doves. And the more deadly your weapons are, the more doves you have in equilibrium. And because like these antlers are very fatal, you have actually a very good ritual going on. Like most of the people stick to this ritual and are doves in this stage.
Okay, actually, we're at the time here. Maybe we can have one more question.
Yeah.
Maybe.
Yeah, okay. Just curious about your model, right? Like it seems to like individual level. I wonder if you can move up to like group level, to the state level, like international relations, for example. Can the model like actually model international cooperations or between institutions? Or it's only individual, like the model limits to individual level of evolution game theory. Can you move to international system?
Yeah. I mean, people might differ here, but I would say the model doesn't care too much who are the individuals who make these decisions. Like, particularly, it could be a government who makes these decisions. Still, the government should think about, okay, what are the incentives of the other governments? And so the very same logic that drives individual decisions should also, to some extent, apply to how governments make decisions.
What kind of like pragmatic insights have come out of this sort of maybe like designing better institutions or something?
Yeah. Okay. Again, I should say two things. Like the reason why we do explore these things is like we would like to understand things better. Like we don't have this immediate design motivation. But having said that, like I mean, game theory in general has had huge applications. In fact, perhaps the most well-known is like how you design auctions. Like, are you well aware of this example? Like, imagine like you have this item and you want to sell it to many people. And now the question is like, how do I design this auction such that the revenue is maximized? And if you have this problem, like, okay, then you suddenly need to make a game theoretic model. Like, for assuming I have these rules in place, what will be the equilibrium? Assume now I have these other rules in place, what will be the equilibrium? And then your goal is to choose the one auction that actually maximizes your revenue.
Okay, it seems like a lot of discussions, and thank you so much, Dr. Hilbe, and thank you for coming. Thank you, everyone.